Hi everyone and welcome back to Physics 2A. Today we are going to be looking at kinematics in 2-dimension now. So last week we talked about kinematics in 1 dimension, just on the x-axis, and now we'll be talking about it in 2 dimensions. Okay, so let's go ahead and get started. Okay, so I wanted to give you guys a quick example of what I mean when I say motion in 2 dimension. Okay, so say that we are in a city probably much larger than we are, okay? And we have these little grid blocks, okay, or city blocks, okay? So in a city, there's kind of like a grid block system, okay? And we want to get to some destination, okay? And we are way over here, okay? And say that we have to walk. So we want to know how far we're going to have to walk to get to our destination. So we would have to walk 9 blocks to the east. Okay, so starting here, we have to get all the way over here to 9 blocks, and then we'll have to go 5 blocks to the north. Okay, so starting here, we'll have to go up north, 5 blocks. Okay, and we want to know the total distance that we need to travel. Okay, so we could calculate this by saying our distance would be our 9 blocks plus our distance to the north as 5 blocks. So now our total distance is going to be 14 blocks. Okay, and again, that's our distance that we would need to travel from our starting point to our destination. Okay, so this is what I mean by motion in 2 dimension. These are completely separate axes. Okay, we can't just go straight there like we would like to. We can't walk, I mean, I guess you could walk through some buildings and maybe some of these are parking lots, who knows, or parks, okay? But typically we can't really do that. So the fastest way would probably be to walk around like this, okay? Now, if we were in a helicopter, say, like in this next example, we could go straight there, okay? And when we are going through and analyzing our motion in 2 dimensions, we can start looking at what is called displacement. Okay, and hopefully you guys remember that from last week, displacement. Okay, so now we are going to, look at that in a different way. Okay, got my pen. No, I don't have my pen. There's my pen. Okay, so again, I just wanted to remind you guys of the Pythagorean theorem. Okay, and that states if we have a right triangle like this, we can calculate all the sides. If we have, say, one side here, A, and we have B, we know those. We can calculate that third side through this equation. You might know it better as C squared equals A squared plus B squared. Same thing, okay? Just wanted to remind you guys of that. So if I were in a helicopter and I wanted to know how many blocks I would have to travel to get from my starting point to my destination, I can do that through the Pythagorean theorem, okay? So you might not think that we use math all the time, but we definitely do, okay? So if I wanted to solve for that, I know it gives me the answer, but we can still do this on our own. So if I'm calling this C, okay, my A is 9 blocks, so I'm going to say 9 squared, and my B is 5 blocks. Okay, so 5 squared. Okay, use your little calculator. Okay, and you can also square root both sides right from the beginning. Okay, so my C is now going to be, well, it should be 10.3. I guess I could actually do this and check. Let me do that. 5 squared. Yep, 10.3 blocks. Oops. Oh, it's getting real messy there. Sorry about that. Okay, so now I know my distance here. Okay, Now again, this is going to be my displacement for when I'm walking on the outer edges. So when I'm walking my 9 blocks east and then my 5 blocks north, my distance again was 14 blocks. What in the heck? Blocks. Sorry, my pen is kind of acting funny. And my displacement, okay, and we can call that delta x, okay, is displacement. It is not picking up everything. Displacement. Okay, that is going to be that 10.3 blocks. Okay. All right, so now that we have a basic foundation of that two-dimensional motion, I wanted to kind of let you guys know, or kind of remind you guys, hopefully, of the independence of perpendicular motions. So like we just saw, maybe this one is a little bit clearer. Like we just saw, I had to move 9 blocks to the east and then 5 blocks to the north. Okay, two completely separate motions. So one of them is moving in the east direction, one of them is moving in the north direction. Okay, so these are two completely independent motions. Okay, so that's what I mean when I say these perpendicular motions, that they're independent. Okay, so this horizontal and vertical components are independent of each other. And when I say independent, they don't affect each other. Okay, so say we are taking a ball in free fall, just kind of dropping it, and we're taking a ball and throwing it. Okay, so in each of these cases, in these balls, we are experiencing gravity, okay, that gravitational acceleration. Okay, so in both cases, we have this y direction. Remember, this would be our y direction if we say x, y, just like that. Okay, saying this is in our y direction. So that's what this red ball would experience, would only be gravity. Now, if I'm throwing this blue ball, okay, and I'm throwing it in the x direction initially, okay, it's still going to be experiencing some kind of motion in that y direction due to gravity on Earth, okay? So these motions are completely separate. Okay, they're independent of each other. Okay, so remember in free fall, it'll just, we start here, it'll just fall down just like that. Now, in this other case, where I throw a ball in the x direction, it'll kind of get off like that, right? If you've ever thrown a ball, which probably most of us have, thrown something, okay, I guess it doesn't have to be a ball, thrown anything, it'll eventually go back down to earth and fall down, okay? So this is the type of motion that we want to be able to describe through physics, okay? So I wanted to first get you guys, or remind you guys again on displacement in two dimension. Okay, so we just talked about that here with our helicopter. He's traveling some distance, which actually happens to be our displacement if we were having to walk on the outside. Okay, so suppose we have two vectors, like in this diagram here, R1 and R2. Okay, so we have two vectors that represent some point. Okay, so say we have P1 and P2. Okay, so we would typically see it like there's one and there's one. Okay, and we can describe these 2 points using vectors like we have here. Whoops. Okay, that one's a little bit off, but you get the gist. Okay, now our displacement, and that's a lot of times what we're going to be looking for, it's going to be this delta r. Okay, so delta r, or we can call it delta x, doesn't really matter. Okay, we just want to remember that this is now a vector, okay, because it has a magnitude and a direction. So it is a vector. We would take our final point, or our second point, r2, that second vector, and subtract our initial vector or our initial point, r1. Okay, and so this is what defines our displacement between two vectors. Okay, and we can do that with anything. So we can have some kind of path that we're traveling in, just like this guy here. And we would do the exact same thing, take our points, okay, our point TI and TF, or P and Q, okay? It's describing the T's as times. And we would create little vectors and then find our displacement. Again, that delta R. Whoops. Okay. And again, our displacement is still in the SI units of meters. I just wanted to get you guys familiar with this displacement concept in 2D. Okay. It's very similar. Okay. So moving on, we can do that exact same thing with velocity vectors now. Okay. So if I'm looking at some XY axis and I have a velocity vector, okay, I have a velocity that's going in this direction here. I can now break that down into its components in the X direction and in the Y direction. Okay, and this is how we do it. We do it the exact same way that we were doing breaking down other vectors in module 1. Okay, do it the exact same way, but now we're just going to call that vector a velocity vector. Okay, so it's the exact same idea. So say I wanted to relate, let's see, the magnitude of my velocity to my X and Y components, okay? So that would be using the Pythagorean theorem, Pythag theorem, again. So I can say V squared is going to be equal to my X component, whoops, that should be Vx, sorry about that. Get my pen back if I can. There we go. Okay, Vx squared, and then my y component, Vy squared. Okay, and then we can, of course, solve V equals plus or minus square root of Vx squared. That's hard to read. That Vx plus Vy squared. Again, all in that square root. Okay, so that's one way I can determine the magnitude of the velocity vector. Okay. Now, what if I wanted to know this angle here? Okay, that will be using trig. So we can use our trig identities to do this. Okay. And again, say I know this guy and I know this guy. I can solve for my theta. So I'm going to say I know my opposite and I know my adjacent. Okay, and so that's going to be TOA in the SOHCAHTOA. So that is going to tell me I can have tan theta equals my opposite, Vy, over Vx. Okay, and then I can solve for that theta, that angle. Okay, by taking the inverse tangent of both sides or the arctangent of both sides. Whoops. Tan inverse of my Vy over Vx. Okay, so now I can describe this motion of my velocity. Okay, and if you don't have, say you need to solve for these, okay, that will be very similar. You'll be using your trig identities again, okay, but again, you'll have to know either this guy or this guy. Okay, so you'll have to kind of look at your trig identities and see which one will work, okay, to solve for what you need. Okay, so again, breaking down the velocity vector is the same thing as breaking down any kind of vector. Oops. Okay, any vector. Okay, same exact thing. And we can do this with acceleration as well. We typically won't see any acceleration in the x direction. A lot of times we'll be looking at acceleration in the y direction because that is due to gravity. So that is going to be typically what we'll see. But anyway, let me move on to what we really want to talk about in this section. Okay, we are going to be looking at projectile motion. Okay, so what is projectile motion? Projectile motion is like I was just talking about. Say I have a ball and I throw it and then it falls to the ground. Okay, that's called a projectile motion. Okay, so it's any kind of motion of an object that's thrown or projected into the air, and it's only subject to acceleration due to gravity. Okay. I've got a couple of definitions here. The object being projected is called the projectile. So that would be like my ball. And its path here, the path that it takes, is called its trajectory. Okay. So we'll be doing this in our 2 dimensions. Okay, here in a second. And I wanted to point out that we, in physics, we typically claim that air resistance is negligible, okay? So this is one of those like hand-waving things that us physicists do. We say, it's fine, we don't need to pay attention to friction, and that's exactly what air resistance is. It's a type of friction. Okay, so we are gonna say it's negligible, so we're not going to take that into consideration when we're looking at these projectile motions and such. Okay? So I wanted to first remind you guys of our equations of motion in 1 dimension. Okay, so this is a list of all of these equations in 1 dimension. Okay, so we've got our position, we've got our average velocity. Let me write V average. Okay, we have our velocity. With respect to time, we can find it. We have our position, okay, and another velocity. So we've got quite a few equations here to consider, okay? But now what we're doing is taking these equations and converting them kind of into 2 dimension, okay? So first, I wanted to give you guys again the idea of projectile motion. Okay, so say we have some ball that's kicked up into the air. Okay, so we will take our beginning position as y equals 0 and x equals 0. That way we just have some kind of starting point and we don't have to put it at 10 or whatever. It just makes our lives easier to just put it at 0. Okay, so we are saying our x and our y initial values, should put a little knot there, are 0 meters, okay? That's typically what we'll do unless told otherwise, okay? So again, we are kicking this ball with some initial velocity, and that's what it says there, that V naught. That's our initial velocity. Okay, let me write some things down here. Initial velocity, okay? And we can break this down into x and y components. So this we can break down into V naught x and V naught y. Okay, so these are, again, both initial velocities, but this is going to be in our x direction and this is going to be in our y direction. Okay, so we can describe everything that's right there. We can even describe that angle that's beginning, and that angle, okay, is going to be our initial angle that the ball or whatever it may be is thrown or kicked, okay, or launched, I guess we could say as well, okay. So all of these values are going to be our initial values, and the way you tell that is again by this little 0 right there, pronounced not, okay. Some people call it 0. Okay, but typically that's what we'll see for initial values. Okay, all right, so a few other things for projectile motion we want to note is that our acceleration in our x direction is typically 0. Our acceleration in our y direction is negative g. Okay, so remember we have the acceleration due to gravity, and we need to define it as ay equals negative g. Okay? All right. And it also has here, in order to break these down into its component forms, our velocity, sorry, I'm kind of getting out of order here, but I just noticed this. The initial velocity in the x direction, okay, we can simply say is v naught times cosine of theta naught. Okay, so we can take our little triangle there, because remember this is v naught, this is v naught x, and v naught y. So now using our trigonomic identities, okay, we can solve for each of these components. If we're looking at magnitude, sorry, ignore that bar there. Okay, so our v naught x, okay, if we want to know that guy, and we know our v naught, and I'll go over this in some examples, so if this is kind of confusing you, totally understand. This is very abstract right now, okay, so I want to know my v naught x, and so I will take my trig identity. I'll say, okay, this is going to be my adjacent, and I know my hypotenuse, so I'm going to use cosine. Okay, so cosine, my pen, cosine theta naught equals my adjacent, v naught x. Come on, work with me here. V naught x divided by my hypotenuse, v naught. Okay? And then as you can tell from just doing a little bit of algebra, you can solve for v naught x. Okay, and then you can do the exact same thing for v naught y. Okay, but now we'll have sine theta naught. Okay? So that was kind of a lot, but we will continue here. So that is just our initial condition here. So as this ball or whatever the object may be moves along, okay, we can do the same thing again. Okay, now what do you notice about let's see, the first thing, let's look at our v component in the y direction. Okay, so our velocity in the y direction, what do you notice as I move along here, as I go from this point to this next point? I'll give you a second to think about it. What do you notice about my velocity? Okay, so for those of you that went ahead and did it, let's see if you did the correct thing or said the correct thing. Okay, so my velocity here, you can see the length of my arrow here is much greater than the second one. Okay, so my velocity as I move along this way is getting smaller. Okay, and then we reach to this peak and you can say, oh, my velocity is 0 at my peak. Okay, that's the exact same thing in free fall. Okay, so in free fall, when we were looking at a ball and it went up to some point at my maximum, it slows, and then basically stops. Okay, theoretically, right? It stops and turns around and goes back down to where it began, or all the way to the ground. Okay, so at that peak, we see that our velocity is 0. Okay, so that's the exact same thing in our projectile motion. Okay, now do you notice anything different about our velocity in the x direction? I'll give you guys a couple of seconds to look at that one. Okay, so if you guys can tell, our velocity in our x direction, if you look at these arrows, okay, they don't change. They stay the exact same. Okay, so our velocity in our x direction remains constant throughout the entire projectile. Okay, and this is again that idea that the x and the y directions of motion are completely they are completely independent of each other. Okay. All right, so hopefully that made some sense. Okay, so let's move on to our next slide here. And kind of looking at that projectile motion again. Okay, so this is an example in your text where a guy is kicking a soccer ball and it goes through this projectile motion. Okay, I just wanted to point out that we can analyze this step by step like we did in this last one. We can do the exact same thing. Okay, so if I want to know, let's say 1 second after the ball is kicked, I can do that. I can say, oh, it is right here, or oh, it's right here. Okay, and analyze that motion. I can figure out my velocity, my x component, my y component. I can figure out all of this stuff at each individual point. Okay. All right. And this is the textbook's pretty cluttered way of doing so. Okay. So they did it every, I don't even know how often, but pretty often. But again, you can see that same exact thing where our velocity vector in the y direction gets smaller as we get to the top. And then again, v naught y, or I'm sorry, vy at top is 0. We can see that. Okay, and so our velocity at that point is purely in that x direction. Okay, and again, our vx stays the same the entire time. Okay, and this is them kind of showing you in components and breaking it down further. Okay, like we were doing earlier. Okay. But again, it's the same idea as what we were just looking at. I just wanted to show you that it is universal. Okay, this projectile motion. This is your x and then your y. Okay. All right. So I want to get you guys to understand something when we are looking at projectile motion, okay, and looking at the effect of velocity. Okay, so if we have, say in, okay, if we have something like this here in part A, okay, we are changing our velocities. Okay, so we start at 30 meters per second, and then we go to 40 meters per second and 50 meters per second. Okay, so think about this way. If you are going to kick a ball, okay, and you only put a little bit of effort into it, okay, so just a little bit of force, our starting velocity is going to be smaller, okay, and the ball won't go very far, right? That makes sense. And if I put a lot of effort into it, if I kick really hard, therefore creating a larger starting speed of that ball, okay, the ball is going to go farther, right? So that's exactly what this is showing you here in part A. Okay, so if we have a smaller velocity, smaller starting velocity, our distance that it travels is going to be smaller than if we had a larger velocity starting. Okay, that's all this part A is trying to show you. Okay, now this is also, this distance that it goes is also dependent on the trajectory or the angle at which it is hit or kicked or thrown. Okay, so in part B, that's what we're looking at. We're saying our velocity is going to be 50 meters per second no matter what. Okay, but now we're going to be changing our angle at which we kick the ball. Okay, so if I kick it at a 15-degree angle, it's going to go about this far. Okay. And if I kick it at some like middle angle, I would say, so about halfway when we're looking at an XY graph, okay, this is about halfway between 0 degrees and 90 degrees, that's 45 degrees, okay? This is gonna be like optimal kicking here because that is gonna send it very far, okay? Now, if I kick it to where the angle is more like this, say that's 75 degrees, okay? The ball is going to go up really high, but then it's going to land pretty close to us. And again, that makes sense, right? Okay, so I just wanted to kind of get you guys to understand that conceptually, okay? And there is an equation here. I'm not sure if we're going to really look at it, but there it is just in case. So our radius or our distance that the ball travels is based on the square of the velocity, initial velocity, okay, times the sine of 2 times the angle theta 0, okay, divided by our gravity, okay? So again, I wanted to get you guys to understand this conceptually, how it changes our outcome, okay? All right, so I wanted to give you guys kind of a list of our kinematic equations for this projectile motion. Okay, so it's kind of a lot, but I kind of want to dissect it a little bit at a time. Okay, so let us first go to our horizontal motion here. So our horizontal motion says that our acceleration in the x direction is 0. Okay, remember when I said that when we're looking at trajectories, we're only going to be considering our g, okay, and that is in our y direction, our acceleration in our y direction, okay? So we won't have any acceleration in our x direction. So we're saying that our acceleration in our x direction is 0, okay? So that's the first point we want to make. Next, if you remember looking at, well, we can look at this plot, that our velocity in the x direction remained constant the entire time. Okay, so that's going to be another thing that we want to make sure of, that we mark down. Okay, so our velocity in our x direction is going to be the same throughout the entire thing. So we say our velocity in our x direction equals our velocity initially in our x direction. Okay, all right. So then we have our other equation of motion for our x, which is just going to be our final x, okay, equals our initial x plus vxt. Okay, so our velocity in our x direction times time. Okay, so this is saying if I want to know where my ball is going to end up, okay, and I start with my ball at this point, and usually we'll just claim it's 0, right? It's going to be equal to my velocity at x, or I'm sorry, my velocity in my x direction, or v naught x, because those should stay the same, times whatever time I'm looking at. Okay? Okay. So now moving on to my vertical motion. Okay, so we know that we're having some kind of acceleration due to gravity, right? So I'm going to go ahead and state that first and foremost. My acceleration in the y direction is negative g, okay? So it's going to be negative 9.80 meters per second squared. Okay, so that's going to be my first claim. Now, I can use my previous equations. Let me go back to here. And I can use all of these to define my y values for these. Okay, so I start plugging things in, and I get this big list of equations. Okay. All right. So they're all very similar to what we had in one dimension, okay? But they are now defined as in the y direction, okay? And we plug our a in for that g value. So instead, normally we have some positive at here, okay? So we're plugging in our ay. So remember our ay is negative g. So we're plugging that in for our a there. So that's why we have a negative gt right there. Okay, and so on and so forth with these other ones. Okay, let me erase that real quick. Okay. So I also wanted to quickly point out these, which we looked at earlier, but I just wanted to kind of remind you, okay, of how to find your magnitude of the velocity, and a lot of times it'll say your direction, okay? All right. Okay, I know this was a lot. I will probably upload this as like a formula sheet or something, just because it'll be a lot easier to read, okay, rather than just on this PowerPoint, okay? All right, again, I wanted to lay out our constraints. Okay, so this is basically what I just went over. Our velocity in the x direction is constant, okay? And our acceleration in the x direction is 0. Okay, we went over that. Our acceleration in the y direction is negative g. That's just plain free fall, okay? Our ay and our y are identical to free fall, so it acts just the same, okay? And so remember, look at that in 1D, okay? Our projectile motion, we say that there's a superposition of the motions in the x and the y directions, meaning there is the independence. So I'm going to write that instead. Independence of the motions. And yes, I made this PowerPoint, but sometimes I change words. Okay, so there's the independence of the motions in the x and the y directions. Okay. The one thing that is shared between all of these equations, if you notice, is our time. Okay, so we have time in a lot of these equations, and that is shared throughout all of them. Okay, so there's no time in the x direction or time in the y direction. That doesn't make any sense, right? There's just time. Okay, and until we can have a time machine that takes us back in time, there's no negative time. So time is shared between the equations, and it's positive. I guess we can just say that off the bat. Okay, so if you ever are trying to solve an equation and you get a negative and a positive value for time, know that that negative value out the window. Okay, that doesn't make any sense for us in this physical world. Okay, so if you ever get those two different answers, a positive and a negative, throw out that negative. Okay, because time is always positive. Okay? All right. Now I have a quick thing to how to analyze projectile motion, so like some steps. First things first is you're going to sketch that path of the projectile path. Okay, so if I'm looking at a ball and it's dropped from here, or not dropped but thrown from here, and it goes like this, I want to have some general idea of what I'm looking at. Okay, so sketch it. Then you want to break it down into your horizontal and vertical components. So I'm going to show you some examples, of course, but just to kind of get you guys rolling is you want to make sure you're breaking that down into the vertical and horizontal components. So I'm going to call it the x and the y components. Okay. You can also break it down into your velocity, or your velocity into components. So your initial velocity, you'll want to put your v naught x and your v naught y. You'll want to get those out. And this is important. You want to treat these horizontal and vertical motions separate, okay? Because remember, they are independent of each other, okay? So you want to make sure that you're doing that, okay? Then you'll want to determine which kinematic equations that you need to use for the horizontal and the vertical components, okay? Solve for your unknowns in both of those motions. And then you can combine those motions to find your total displacement and your velocity, okay? And you can find your magnitude and your direction for them, okay? And for your velocity, that may include some kind of theta as well, okay? So again, I'm going to go into this, and then that will be in the next PowerPoint, or not PowerPoint, in the next video, okay? So bear with me. It's going to be a little bit of doing, okay? It's not going to be simple, you know, plug and chug type of math, but once you understand it, they'll be pretty repetitive, okay? But I'll show you a few examples to get the ball rolling here, okay? All right.